Okay. So probability is the measure of how, we're going to put the word likely in the blank, how likely an event is to occur. The next bullet defines sample space as the set of all possible outcomes. And it goes on to tell you that the sample space of a valid probability function adds up to 1. So we've got two different situations here, and I'm giving you two different examples. This is some probabilities and this is some probabilities. If you wanted to decide if it was a valid probability function, you'd add all these up. It's supposed to add up to 1. If you look at this one, that one's a valid probability function. Let's go over here and look what we get if we add all these up. That one is not. A valid probability function needs to add up to exactly 1. Okay, for equally likely outcomes, this next one is actually talking about the definition for probability. The probability of an event is the, and in the blank you need to put ratio, R-A-T-I-O, ratio of the number of favorable outcomes to the total number of outcomes. Now, I do my probability a little differently. Here's how I define probability. You know it's a ratio, which means you've got a number being divided by another number. Okay, on the top, the numerator is what we're considering a success. Could be heads, could be a red crayon, could be a blue marble. It could be the number, it could be a prime number. Any of those things we can consider a success. On the bottom are your total possibilities. So probability is your success over your possibilities. So let's see how that works. Start out with simple events, which just means one probability. And we have a jar with 32 red and 28 blue. So we have 60 marbles in all. What's the probability that we randomly select a red? Okay, so the way this works, if you remember the definition for probability, what we consider to be a success is on the top. How many ways can that happen? 32. 32 red. On the bottom is your total possibilities, your sample space, which is 60. When reduced, 8 over 15. Number 2, they give you the word restoration, which has 11 letters, and they want to know the probability of randomly selecting a vowel. So vowel is what we're considering a success. If I look at restoration, there's 5 vowels. Total possibility 11. That can't reduce that one. Correct. Okay. A day in the month of January is randomly selected. What's the probability that you randomly select a prime number? What is our sample space? How many total possibilities are there if we're looking at every day in the month of January? 31. Okay. And of those, I have the primes written over here for you. If we're thinking about the month of January that goes to the 31st, 8, 9, 10, 11, if we're 11 of those are prime, that also won't reduce. 2 dice are rolled. What's the probability that if you add those 2 dice together or sum them up, you get at least 9? So let me show you what you need to do if you're ever dealing with a 2 dice problem. This is called a lattice, and this is a visual of anything that or everything that can happen when you roll 2 dice. You know you can get a 1 through 6 on the first one or a 1 through 6 on the second one. And then here is every possible option: a 1 and a 1, 1 and a 2, a 1 and 3, and so forth. Okay, so this will help you with just about any time they ask you to roll 2 dice. Well, first, before we go on, what's the sample space when you roll 2 dice? If there's 6 here and 6 here, 6 times 6 is 36. So we know we're looking at 36 possibilities. of those 36 possibilities, we're looking for the ones that add up to 9. Nothing on this row will even give me 9 here either. 3 and 6, 4 and 5, and 4 and 6 both give me, because it said at least 9, so it can be greater than 9. Okay, so that's my situation for at least 9. 10. If you don't have that lattice, it makes it a lot more difficult trying to get your probability. So that gives you 10 out of 36, which reduces to 5 over 18. We're going to skip 6. We want the probability of a heart or club from a standard deck of cards. Now we know the simple space with a deck of cards, it's 52. And then of those, which ones are hearts and clubs? Hearts and pieces. 6. Half, because you know there's 4 suits, and so those are 2 of the suits, so that reduces to 1. So that's simple probability. Success over possibilities. Notice your denominator is your sample space. How many options are possible? Okay. Let's move to compound. And what that means is actually we'll do complement first, then compound. Okay. Complement of an event is the probability of the event not, so that's what goes in the space, not happening. Okay. Since the sum of all the probabilities in a sample space is 1, the probability of an event not happening, and that, you see that little line in front of E? That means not E. So the probability of that event not happening is 1 minus the probability that it happens. It's called a complement. So if I was talking about the probability of it raining, its complement will be not raining. Okay. And so the probability of all that goes together to make 1, so 1 minus gives you your complement. Okay, number 7, the probability that it will snow tomorrow is 7/20. What is the probability that not snow? Good. I heard someone say the answer, but to set it up, I do 1 minus the probability of it snowing. Okay. Lots of different ways to get that number. Here's how I would do 1 minus 7/20. I know I need to both have a denominator of 20. A way to write 1 with a 20 as a denominator is 20/20 minus 7/20, which is 13/20. If 7/20 is my probability of snow, 1 minus that is my complement. And do you see how 13/20 and 7/20 would go together to give you 1? Makes sense? All right, number 8, a month of the year is randomly selected. What's the probability that it does not begin with the letter A? So not A would be 1 minus the probability of A as your first letter. How often does that happen with months? 2, April and August, right? Okay, so what would be the complement to 12s? It would be 10/12, good. It would be 12/12 minus 10. Or if you reduce it, you're going to get 5/6. We're going to skip number 9. I need to subtract 1 minus 2 12s. So I change my 1 to a 12/12. 12 minus 2 is 10. Just put the answer back up there. 2 dice are rolled. What's the probability of not getting doubles? So we want a probability of not doubles. which is equal to 1 minus the probability that we do get doubles. So go over to our little lattice. What's the probability that you get doubles? Six. 1, 1, 2, 2. Okay, so 6 out of 36. Do the same thing. If I want to change 1 so that it has a denominator of 36, it'll be 36 over 36. Everything divided by itself is 1. So 36 minus 6 is 30. And that reduces to 5/6. Put it equal there. Okay. So that's complement. Think about 1 minus for complement. Now we're getting to compound events, which is 2 or more simple events. Okay, but when you've got compound events, you can either have independent or dependent. Independent means that the one event does not impact the other event or the probability of the other event. They're independent of each other, kind of like what you would think of. If they are dependent, then the probability of A has an impact on the probability of B. Okay, so if they're independent and you want to find A and B, I don't know if you remember this, but when you see the word and, you're thinking about multiplying. Or is an addition, but the and, your intersection, is multiplying. That's if they're independent. You just simply multiply the two probabilities together. If they're dependent, when one event does affect the outcome of the other, it's the probability of A multiplied because of the and, probability of B, given that, straight line down. After the B, go straight line down. And I'm going to translate it for you in just a second. A. When you have dependent events, you have to realize what happened with A has an impact on B, and you've got to take that into account. So what this literally translates to is the probability of B, given that A has already happened. Here it doesn't matter that A's already happened because A and B don't depend on each other. They're independent. Here it matters that A has already happened. Okay? And I'll show you how to use the formula in a little bit, but right now it's enough to know there's a difference between independent and dependent events. If you don't understand the formula, I get that. But if you don't understand, I think even with how we use independent and dependent in conversation. So, like, if somebody told you in history, like, I had a huge vocabulary test, and I didn't study at all, like, none, didn't even look at my notes, and I did not do well. I made like a 40. Would you think that those events had an effect on each other, or would you say, hey, that's one thing that have you think of the other? Well, okay. Well, I think studying does give you a probably dependent. So I don't think those will be independent. Let's see. What would be another example? What if you did something really, really dumb and you were speeding and weren't paying attention to what you were doing? You were on your phone and you're doing 3 or 4 other things and you had an accident. Would you say those were dependent or independent? That's the idea we're trying to get behind. We'll figure out the math that comes with that in a little bit, but there is a difference. Okay? So when we get to independent, so we want we're rolling a dice 3 times. We want the probability of getting a 1 on each roll. So we want the probability of a 1 and a 1 and a 1. And we know they're independent, but think about it. You know they are, so I roll it, I pick it up, what I did this time has no impact on what happens the second time. What I do the second time has no impact on the third. So really all we need to get at is what's the probability of rolling a 1 when you have dice? 1 out of 6, because there's 6 faces. Okay, so the top is going to be 1 times 1 times 1. The bottom is going to be 6 times 6 times 6. 6 times 6 is 36. 36 times 6. Y'all want tendency to put 18. I realize that. But
that's not what we're doing.
Okay, so let me get it over. This one. 1 divided by 260. 26. Alright, a coin is tossed and a day of the week is selected. I'll do this in black so that you can see the difference between the two numbers. What's the probability of getting tails and picking a day of the week that starts with the letter T? Okay, so probability of tails is 1/2. And then there's 2 days of the week that start with the letter T. So that gives you 1/7. Now the rest of these are going to deal with pulling crayons out of a bag. And we've got 8 red, 14 purple, 6 yellow, and 4 green, and that adds up to 32 crayons. So we got 32 crayons in our bag. And if you'll notice, it says that we're going to pull the crayon out and then replace it. Please underline the word replace. Because when we replace them, most of the time that means what we're doing is going to be independent of each other. Okay? We're not changing our sample space because we're pulling out a crayon, looking at it, and then putting it back. So let's see what happens if we try to get a purple then a yellow. So we want the probability of a purple then a yellow. So the probability of a plain old purple is 14. I pull it out, I look at it, I put it back. Now what's the probability of getting a yellow? 6 over 32. And all that's left is a little multiplying, a little reducing. If you want to go ahead, you're going to get 21 over 256. 21 divided by 256 if you reduce it. I really prefer you just leave it as a fraction, but you know, I'm not going to be real picky about that. 14, we're not going to work it, but when you have a minute, go back and make sure that you can get 1 over 32. All right. 15, we want to get 2 purples. Okay, so probability of getting purple when I reach in is 14 out of 32. And I want to get a purple the second time, but just think about what happens. I put it back in the bag. Probability of getting a purple is still 14 over 32, which reduces to 49 divided by 256. And then week 16 is really similar. I'll put the answer here to the bottom right, give you a chance to check your work. So that's kind of how independent works. What you do on the first action does not affect the probability of the second action. Alright, now let's move on to dependent. Using the same crayon example as above, assume once a crayon is selected, it's not replaced. And you might want to make a note, underline not replaced, and also make a note that usually it's called, or a lot of times it's called without replacement. So this time, instead of me sticking it in my pocket, instead of me giving it back, I stick it in my pocket. Right? So what that means is it changes my sample space, and it has an effect on the next action. So if we want the probability of yellow and red on number 17, the probability of getting a yellow is 6 out of 32. But see, I don't put that back in this thing, I keep it. So what does that reduce my sample space? 31. And there's 8 red. So that reduces to 3 divided by 16. Well, like, that would give you an opportunity to work that. How did I get what? Because when I pulled the yellow crayon out, or when I pulled the crayon out, I did not replace it. It was without replacement. So now in the bag, there's no longer 32, there's only 31. Probability of 2 reds. I reach in, pull out a red, there's 8 reds, there's 32 in the crayon box. Or the bag, wherever we have them. Okay, it's without replacement, so I don't replace it. My sample space is now 31. Okay, so think about what happened. I had 8 reds, now I have 7. Oh, I see what you're saying. Somebody else had that question today, too. Yeah. Yes. Since there's 6, that's the probability of getting a yellow, but yeah, you're only pulling 1 out. And then 20, you will get it down to 3 divided by 248. 21 is going to be the last one that we work together. A card is drawn from a standard deck, not replaced, without replacement, and another one is drawn. What is the probability of choosing a heart and then choosing a spade? So my sample space is 52. 13, okay. 12, 13. Okay, my sample space is reduced to 51, so set the card in my pocket, I didn't click on it. So let's say I got a heart on the first time. How many spades are still in the heart? Now, if it had been a heart and a heart, that would have been 12. But since it's a heart and a spade, which that will reduce to 13 divided by 204. And then number 22, the one about the candy board, will reduce to 1.